Hi, my name is Terita, and our chosen research paper is Agent-Based Modeling and Simulation of Mosquito-Borne Disease Transmission, which is authored by Jindal and Rao of the International Institute of Information Technology in Bangalore. In order to understand the motivation for this research paper, we need to look at what mosquito-borne diseases are. Well, it is simply defined as diseases caused by bacteria, viruses, parasites transmitted by mosquitoes. Such diseases include malaria, dengue, and chikungunya, which are commonly heard of. These diseases are menacing and can be life-threatening. In fact, mosquito-borne diseases are the largest subset of vector-borne diseases, which account for more than 17% of all infectious diseases. They have high attack rates, which causes more than 1 million deaths annually. Not only that, but mosquito-borne diseases are re-emerging and expanding to new regions. While this creates the need for proactive solutions for their containment, particularly solutions capable of tracking the trajectory of the infection evolution. This gives rise for the need of models to track the spread of such diseases. However, modeling the complicated relationships among human, mosquito, pathogen continues to be a challenging problem faced by public health experts. There are traditional methods or models that exist, like differential equation model, mean field type models, which have been used by epidemiologists and disease modelers. However, these models fail to capture issues such as distribution and mobility of host and vector population. It fails to incorporate geographical data and weather conditions. It is important to have a model that accurately models the transmission of diseases. This is to help or aid with public health policy making and help with epidemiological studies. All these points are dependent on how closely the model relates to real-life transmission of diseases. Here are some possible research questions the authors might have asked. How do we effectively and accurately model the transmission and spread of mosquito-borne diseases? How can we test the efficiency of the agent-based model in relation to the prior models? How can the proposed APM contribute to low-level policy design? How can the APM be used to test and improve prevention strategies? With those research questions in mind, the authors proposed their solution, an agent-based model APM that overcomes the limitations of the prior models and that adequately captures the spread of mosquito-borne diseases. APM consists of 4 components that are interrelated: the infection model, the mosquito agent, the human agent, and environment. The infection model represents the different states of the disease transmission between human to mosquito and mosquito to human. It was classified into 2 stages by the authors: the incubation period and the infectious period. Incubation period is when a mosquito acquires the pathogen. Mosquito successfully infects the human. The pathogen multiplies inside the host, and when the pathogen reaches a certain threshold, we enter the infectious state. The human starts to show symptoms, and then the probability of pathogen transmission is very high during this period. The authors chose the CO model for the human infection model as seen by the diagram. Susceptible state is when the human agent is vulnerable to the infection by the pathogen. Exposed state is when the individual is carrying the infection but is not yet contagious. The infectious state is when the individual has started showing symptoms and is ready to infect the mosquito. Recovered state is when the agent has fully recovered. The chronic recovered is when the human agent has recovered and no longer contagious but still has some symptoms of the disease. The infection in mosquitoes follows a similar cycle, except for the fact that they do not recover once they have been infected. This design was important so that it is easily generalized the model to a large subset of mosquito-borne diseases. Mosquito agents were characterized by many parameters such as flying speed, the maximum distance, the active periods, and so on. All these parameters were determined to be essential as they directly affect the mosquito population and their behavior relative to their environment. The mosquito model was designed to heavily to be dependent on precipitation data and availability of resources, as these are known to be major factors in disease propagation, and also to closely resemble the mosquito population in nature. Human agents were divided into four general categories based on their mobility patterns, based on where they gather in groups and how often they go near potential mosquito breeding grounds like lakes. Type 1 resembled that of students, Type 2 of office workers, Type 3 of workers who dynamically on the move, and Type 4 of those homestayers. This human agent approximates the mobility patterns across various populations. The smart design of the human agents allow the APM to adequately capture the spatial movements of the infection. This enables us to analyze various intervention strategies to be used. The environment model is structured using geographic information to address space implications in disease expansion and growth. The environment model then combines this with weather information of the location like temperature and precipitation in order to capture disease and mosquito dynamics. The agent-based model was carefully designed and initialized to imitate the characteristics behavior of the mosquito-borne disease.
Hi, I'm Zhonglin Chen. In the last part, Tivita has briefly introduced the background and the new engine-based model presented in its paper. In this part, I'm going to talk about the validation of this model and the corresponding results presented in this paper. As you can see, this section includes four parts, which are simulation overview, parameterization and initialization, and the training of this model and the testing of this model. First of all, I'm going to talk about the simulation overview. To prove the new concept in this paper, the author applied the model to simulate a case study of past epidemic of a mosquito-borne disease. To illustrate the model, in this paper, they used the model to simulate the outbreak of epidemic in the Caribbean and predict the trajectory of the epidemic. Also, for the purpose of demonstration, some parameters are tuned to fit for the particular scenario. And then let us look at the data used in the simulation. They include the epidemic data and GIS data and weather data and census data. This data set are collected from the previous epidemic of the same disease in a similar location to the testing site. After training, the simulation is run for the testing site, and the model will be finally tested on epidemic data from another Caribbean island. We simply called it Presby. Here, the paper assumed that the residents in Presby had never encountered the virus before and had no existing immunity. And then for the simulation, the GAMA was chosen as the simulation platform because of its data-driven ability and intuitive agent-based language. And after the overview of simulation, we are going to present the detail of the simulation. Firstly, before the training data, different parameters like mosquito parameter, human parameter, and so on in every part of the model should be initialized. According to this paper, most values were compiled together from various sources, but we don't get the detail that how they were said to be optimal. And in here, detailed description of the parameters and the sources are listed in the table. However, here we must point out that some parameters like PM, PF, SR are tuned, and due to the lack of any concrete empirical evidence of their values. In this paper, basically, they tune the parameters by trial and errors to give a good fit on the training data. Error was derived with respect to historical and training data, and also um, sensitivity analysis was conducted to determine the effect of every parameters on the model's output, and the more sensitive parameters were, they made sufficiently accurate to reduce error. The first parameter was the mosquito sensory range, SR, which was tested for 6 different values, and the error in fitting was recorded for each value. As shown in this picture, this parameter was found to be significantly sensitive and give best result when it was tuned to 3 meters. The second parameter for sensitivity analysis was the which is the maximum number of meals in a day. It varied from 1 to 3, and the error was recorded. Finally, it was fixed to 1 to minimize the error. As for the other two parameters, that is PM and PF, these two parameters were likewise fixed to 0.2 and 0.5 respectively, as they on average gave approximately constant mosquito population. At the end of training, according to this paper, the training result of this model was well fitted into the historical data. They argue that the error of the small cases was left to account for unreported cases. Finally, in this testing part, the training model was run to check with the actual data in testing site. The results shows the error in count kept really small during the 12 weeks. Therefore, the author argued that this model could provide very accurate result to model the mosquito-borne disease and scale well to different population size. And then in next part, Yang is going to present the left of this paper.
Okay, this is Yang. Next, I will introduce the main strategies to prevent disease transmission via mosquitoes. Basically, there are two strategies, which are centralized strategy and decentralized strategy. The first strategy is called centralized strategy. In this case, there is a centralized organization that make efforts to prevent disease transmission. These organizations can be the governments or some health organizations. The main method of this organization is to reduce the population of mosquitoes. For example, they can detect and eliminate breeding places, cover persistent water source, and supply reliable water to households. Like most public policies, we care about the cost of establishing such facilities. In fact, the centralized strategy is quite economical. Generally, the cost is up to the size of the treated area, and this cost comes to $6,000 US in 2016, which is relatively very low. While next we will discuss about the decentralized strategy. Instead of focusing on the mosquito habitats, the decentralized strategy only cares about the behaviors of humans. In this case, for example, an individual can use repellent creams, wear special clothes, or just stay at home to make himself not be exposed to mosquitoes, and all of these actions can efficiently prevent mosquito bites. The decentralized strategy is also with a very low cost. For an individual, if he chooses to get insecticide treat, he will spend only $10, and for a household, this is $180 if they do indoor residue spraying. Well, next we will introduce the comparison of two strategies. Before which, we need to give some initial settings. And firstly, our total budget is $20,000, and the simulation is taken on a town with 5 square kilometer size. And for centralized strategy, we assume that only 2/3 habitats are found and treated so that our budget is sufficient to cover it. And for decentralized strategy, the random selected households will be arranged to about $220. Okay, now we are ready to show the results of the comparison. First, we focus on the number of agents getting infected, including both humans and mosquitoes. Clearly, this number goes very high if we don't take any strategy. The fact in the figures shows that the centralized strategy is more efficient because it reduces the number of infected agents to a very low level stably within 5 weeks, while decentralized strategy makes it at a higher stable level in more than 6 weeks. Next, we will move our attention to mosquito population. In this case, centralized strategy also performs better. They can reduce this population by 70% and the number of eggs at a very low level. However, decentralized strategy only reduces it by 25% which is in fluctuation. So overall, centralized strategy seems to be a more efficient strategy. Well, that's all we wanted to introduce about this paper, and then now we want to make a summary of this paper. The first is that the model proposed in this paper is full of practical meaning because it can be used to prevent some mosquito-based disease transmission. And the second is that our simulation shows that on low budget, our centralized strategy is more efficient. So that's all we want to talk about this paper. Thanks for watching.